point of this class, lecture, video is to recap some of the things you should already know about stochastic integration and Ito's formula. We're going to apply a kind of unrigorous look at these, a bit like before when we were deriving the HJB equation. We relied on various Taylor expansions in order to derive the Hamilton-Jacobi-Bellman equation from the discrete time Bellman equation. Okay, we want to do something similar. We want to get the HJB equation for a diffusion control problem from a Markov decision process. Okay, so I want to apply some similar ideas with that Taylor approximation idea. So I want to kind of recap what those sorts of Taylor approximations would be when we've got a diffusion process. Okay, so essentially what I'm alluding to is the definition of the stochastic integral and Ito's formula, which acts as a kind of chain rule for stochastic integrals. Okay, so you've already covered these. If you're sitting in the University of Manchester, you've already seen these as in your stochastic calculus course, but I think it doesn't hurt to cover it again. Okay, given that you're given the rigorous treatment of this, and this is a much more heuristic treatment of this theory. Okay, so as you know from your stochastic calculus course, you need a well-defined and well-developed theory of L2 martingales in order to make all of this stand on proper firm footing. And we're going to sort of throw away all of that good work and just try to get the kind of nuts and bolts of the idea. Okay, so this is a recap of stochastic integration. Okay. And what we're going to do is a heuristic derivation of Ito's formula. Okay, so rigorous proofs of these sorts of exercises are not expected, so we're not going to try and come up with the kind of rigorous result. But all the same, I think we should hopefully get kind of the main ideas across. Okay, so heuristic look at stochastic integration to start with. So we're going to let B of t be a standard Brownian motion. Okay, so that's something where each increment of the process is going to be normally distributed as follows. Okay, and any increment of this form, which is disjoint from any other increment, is going to be independent. Okay, now we should want to argue for this first exercise that for a standard Brownian motion, that for all t greater than 0 and for all delta sufficiently small and positive, we have the following terms and approximations. So the first one is that if we sum from a time 0 to t, taking gaps of size delta, we sum at b of t plus delta minus b of t, we're going to end up with just the Brownian motion at time capital T. Okay, and we have that if we sum up times 0 delta 2 delta all the way up to t, okay, that b of t plus delta minus b of t squared now, okay, is going to be equal to capital T, or approximately equal to capital T. Right? Now, if this was a deterministic process, then this would definitely vanish away to 0. But since we're dealing with Brownian motion, which is a much more volatile process, then this is going to give some positive answer. In fact, it's going to give a fixed number, capital T. All right. So why are these two things true? Oops. Well, for the first one, the first term here, notice, is an interpolating sum. So when I go from one sum to the next, notice this is going to, in the first term, this is going to be the last term in the second sum. Okay, so we basically can kind of cancel out diagonally as we sum up. All right. So the first sum is an interpolating sum. So if you wrote it out term by term, you'd find a lot of things cancel out. And so what's only going to survive is the very first term on the right-hand side and the very last term on the left-hand side. The last term on the left-hand side is bt, and the very far right term in this sum, and the first term will be 0, and so it's just excluded. Okay? So gives the answer there. further, each term in the second sum so in this guy, each of these terms is the square of a normal distribution, okay, with variance delta, okay? All right. So each term in the second sum is an independent, identically distributed random variable, okay, with mean delta. Okay, so the mean of the square here is delta, okay, or in other words, the variance of this random variable with these times is delta, okay? So if we're summing up a lot of things, okay, which have this same mean delta, okay, then we can apply essentially the strong law of large numbers to these guys. Okay, so notice we're summing up delta t terms, so t over delta terms here, okay, and each of them has mean delta, so we're going to end up with t overall. So t divided by delta terms, each mean delta, okay, so we're going to get delta times t divided by delta, okay, on average, so an average of t, and since it's ID random variables, okay, we can apply strong law of large numbers, and this equality is going to get tighter and tighter. Okay, so summed by the strong law of large numbers, this term is going to go to capital T as delta goes to 0. Okay, that's the main idea of that first part. Okay, next exercise, we're going to begin to do some integration with this. Okay, I'm going to do this in a very unrigorous way. Okay, so discuss why it's reasonable to expect that if I do the sum of a sum a little bit like this one, but I'm going to add a bit of a coefficient at the front here. In this case, I'm going to add a sigma x of t. In the case of each of these terms, I'm going to do the same sum, but I'm going to multiply, okay, by mu of xt, all right? Then it's reasonable to expect that I get some limit out, all right, as I let delta go to 0. So specifically, I'm going to call this limit the integral from 0 to t of 0xt dbt, and in this case, okay, notice that by the strong law of large numbers, each of these terms is approximately equal to delta, okay, so it's going to equal just the distance between this term and this term, okay, and so should approximate the Riemann integral, or in specifically in this case I should probably say like Lebesgue-Stieltjes integral of mu of x of t dt. Alright? Okay. So let's discuss this guy. Okay? So we look at this first term. So let's answer that quickly. Okay, so the first term is the, should I say, Riemann-Stieltjes approximation. For the integral. Okay, in other words, if I wanted to an integral of the following form, 0 to t, f of t dg of t, okay, then I could approximate this by the sum so I take each of the rectangles, okay, where the height of each rectangle is f of t. I'm going to assume that the width of the rectangle is given by the difference, not just delta, but the difference between g of t plus delta minus g of t. Okay, so that's the kind of approximation you deal with when you're doing a Riemann-Stieltjes integral. Okay, so given that these approximations can be made exact, we could guess that maybe this can be made exact as well. Okay, of course I'm throwing caution to the wind because usually g of t is assumed to be a finite variation process, and when the Brownian motion isn't a finite variation process, so one really needs to work a lot harder to get this rigorous. Okay, then for the second term, we've said that this is approximately equal to delta. All right. So as delta gets smaller, this is going to get closer and closer. Okay, or this divided by delta is going to get closer and closer to 1. Okay, and that's because in each case we've got a normal, the mean of a normal distribution here. Okay, whose mean is delta. So if I sum up enough of these, and this doesn't move too fast as I do that, we expect that we could replace each of these expressions in here with delta. All right. So if I can do that, then I'm going to end up writing down exactly the same thing, the Riemann-Stieltjes approximation with mu x of t here instead of f of t, and with dt here, okay, or in this case delta here, instead of this expression. Okay? All right. So for the second term, this is approximately this. So, so the sum over t of mu of x of t, b of t plus delta minus b of t is approximately the integral from 0, well, let's say like this, is approximately the sum of x of t delta, okay? Because if this doesn't change too fast, then we could think of each of these being approximately linear. Okay, we're essentially taking these kind of rectangles and then looking at the heights being mu x of t. All right, so that's very unrigorous, but it gives us sort of essentially the key ideas which are going on here. All right, so essentially because these sums approach a line, okay, then we'll apply this as if we're integrating in respect to something linear. Okay, dt. All right, okay. Right, enough about that. So, now let's get the idea of where we've got some diffusion, okay? So something where we've got a process which is driven by some drift and some noise, okay? So, if we inductively define x of t by the following recursion, where we'll let the next time x of t plus delta be the previous time, plus some small normally distributed noise times some coefficient, plus some small drift term given by the length of time, plus some extra coefficient here, okay? Then discuss why we expect x of t to be approximately obeying an equation of the following form. X of t equals x of 0, integral from 0 to t, sigma x of t dB of t, plus integral from 0 to t mu of x of t dt. Okay? All right. So why might that be true? Well, what we can do is we can just sum these terms over delta. Summing over t from 0 to, say, t minus delta. So we go 0, delta, 2 delta, all the way up to t minus delta. Okay, it's going to give x of capital T minus x of 0 is equal to the sum of t over the range I just described. Okay, and x of t minus delta minus x of t. So again, we've got this these interpolating sum. Okay, that's just each diagonal term cancels out in this. Then I could replace this with this expression here, and I'm going to end up with the sum over t over these values of sigma x of t b of t plus delta minus b of t plus the sum with the same set of values of this term, mu of x of t of delta. Okay? And then, as I've given above, like I said, as we let delta get smaller, this should converge to some integral. An integral which we're going to say is with respect to Brownian motion. Okay, so if you believe me there's some in it, then I'm going to get this. And here, again, we've got a Riemann integral in the traditional sense. So this we expect to converge to this. Okay, so again, we're assuming that there's some sort of limits here. But if there are, then we'd expect something that is satisfying this recursion, or even approximately satisfying this recursion, should then obey an equation of this form. Okay, right. So there we have what we'd call a diffusion equation, okay, or stochastic differential equation. All right. Okay. Now, all right. So now we've given the idea of a stochastic integral. That was essentially this exercise, and we've given the idea of a stochastic differential equation, which is this exercise. Okay. Now I want to give the idea of something called Ito's formula. All right. So that's sort of like a chain rule for stochastic integrals. Okay. So here, let f be some twice differentiable function, and argue that if I let x be this process here, okay, argue that then f of x of t minus f of x should be approximately given by this expression. All right. So here I've picked up the terms which are to do with the deltas, and here I picked up the terms that are to do with the Brownian motions. Okay, so this is somehow going to give me an integral with respect to time, perhaps. This is going to give me an integral with respect to Brownian motion, perhaps. Okay. Right, so let's have a go at that. So again, we could do our kind of Taylor approximation idea as before. Okay, so we're going to apply a Taylor expansion or a Taylor approximation. Okay, so specifically f of x of t plus delta minus f of x of t. Okay, if we're going to let x be given by the term above, just here, this one, then I have to substitute in for that x of t plus delta, x of t plus these terms. Okay, so let's do that. So this is going to be f of x of t plus sigma x of t, b of t plus delta minus b of t. Okay, and I've forgotten my mu terms, plus mu of x of t delta. Okay, so that's just substituting in the appropriate value for this from the recursion that it satisfies. I have to minus off f of x of t. Okay, so then I minus off f of x of t. Right? Okay, so far so good. So we've just substituted in something for x of t plus delta. All right, and now I'm going to apply a Taylor expansion to this. Okay, so what I'm going to do is look, the error term in this between here and here is given by these terms. Okay, so what you get when you do a Taylor expansion, I'm going to do the Taylor expansion for the first two terms, and then what's going to be remaining is the error, essentially. Okay, so let's do that. So essentially got the first derivative of this then times the error. Okay. At this point, I'm just going to sort of skip the x of t's in the sigma and the mu. It just makes things a little bit shorter. So the error here is going to be mu of delta plus sigma times bt plus delta minus bt. Okay, so that's just this error term here. Okay, and then we get the second derivatives, which is going to give me f double dash of x of t divided by 2, and I'm going to get the error term squared. Okay. Oh, sorry. Okay. And then I'm going to have things which are going to be little o of delta. Okay. Right, you have to think about why that's true, but it is. Okay. So why have I gone up to the second derivative? Normally, if we're going to do a Taylor approximation, or we wanted to approximate something like this, we'd only need first derivatives, not second derivatives. Okay. But notice here in this term, we're going to pick up that something that b of t plus delta minus b of t squared. Okay. And we know that if we kind of sum these together, or we look at them compounded, we know from the above exercise here that that's actually going to count for something. Okay, because there's a Brownian motion involved, the sums of squares actually count. Okay, if we get to higher order things, they're not going to count, but if we sum up squares, then we're going to get something that counts. Okay, so this term summed up a few times is actually going to compound. All right, so we're going to need the second derivative term. Okay, but the other terms are going to kind of not matter. All right. Okay. So then we can kind of expand out these kind of brackets. Okay. So what we're going to get is we're going to get the same term as before. Here. Okay. And I notice that when I square this out, I'm going to get a mu delta squared, which is little o of delta. And I'm going to get a mu delta, two lots of mu delta times sigma bt plus delta minus bt. Okay, so that's something that's of order delta. And notice this is of order sort of square root of delta. So we're again going to get something little o of delta. So the only term that's really going to count and not get absorbed into this little o of delta is just the sigma times b of t plus delta minus t squared term. All right. So if I write that out, I'm going to see the only thing that really survives and isn't little o of delta is going to be sigma squared dot b of t plus delta minus b of t squared. All right. And then we said that actually these are kind of this is sort of the variance. If I take an expectation here, this is the variance of a normal distribution with variance delta. Okay, and so this guy is approximately equal to delta. Okay, so I could then absorb that over into this kind of delta squared term. Okay, so notice that I'm essentially going to recover from here something that's f double dash x of t divided by 2 sigma squared times delta. In other words, I'm going to get this term. From here, I'm going to get something that's f dash of x mu, that's this term. Okay, and then finally I'm going to get f dash of x mu b of t plus delta minus b of t, which is that term. Okay, so we've essentially picked up all the terms that we wanted. Right? Okay. So that's all fine. So essentially got this is equal to that plus stuff that is order little o of delta. Okay, so things that if I divided by delta would go to 0. Right, so then the next part and the final part argues that f of x of t minus f of x of 0. Okay, so if I've got x of t that's satisfying that stochastic differential equation from before, then if I take f of that, then it should satisfy this equation, right? So let's just recap that if I've got x, which satisfies this equation here. Oh, sorry. That satisfies this equation here. Okay. Then, if I apply some function to it that's twice differentiable, then it should satisfy this equation. All right. And this is called Ito's formula. All right. Well, so we've kind of done our Taylor approximation. Well, why is this true? Oh. Essentially, we're going to do our idea. We've done our Taylor expansion. Now we're going to sum up from this expression. Notice that if I summed up this term, that would be the same, approximately summing these. Okay, so f of x of t minus f of x of 0 is the sum over t, starting at 0, then going to delta, then going all the way up to t minus delta. Okay, so summing over that set of f of x of little t plus delta minus f of x of t. Right? And then I've got an approximation for these differences. That's this given up here. Okay? So this is approximately equal to the sum over t, over the same range, of these terms up here. So we're going to get a f dashed of x of t mu, or mu x of t, okay, plus f double dashed x of t divided by 2 mu of xt squared, and all of that is times by delta, plus this remaining term, plus the sum over t over this same range, okay, of these terms. F dash of x of t times sigma x of t times b of t plus delta minus b of t. Alright, so now I've just substituted in this expression, okay, into here. Alright, and then we know that if I have some function times delta and I sum it up, okay, I'm effectively taking the Riemann-Stieltjes summation here, so it should converge, or at least be approximately equal to the integral from 0 to t of f dashed of x of t of mu of x of t plus half double dashed x of t divided by 2 sigma x of t squared dt. Similarly, okay, by our exercise just above, we also know what happens to these kinds of terms. All right? That if we look at the differences of the increments of the Brownian motion and then times it by something, it converges to some sort of integral. Okay? So specifically in this case, it's converged to some sort of integral of f dashed of x of t of sigma x of t d, where the increments are given by Brownian motion dB of t. Okay? So in other words, we're going to arrive essentially at this formula. Okay? So this is the kind of analogue of the chain rule for a stochastic differential equation. All right? And notice again that we can look at this in terms of some sort of Taylor approximation idea. Okay, so that same Taylor approximation idea is going to be something that we're going to use when we look at how the Bellman equation for a diffusion process or for a stochastic differential equation. Okay, so next time what we're going to look at is we're going to have maximization and minimization. Okay, but the Planck equation now, the evolution of the state of the system is going to be some sort of stochastic differential equation. Okay, all right, so we've got that to look forward to next time. Okay.